Hi, this is Track A Mathematics. Today we are going to look at Part 3, Calculus and Backpropagation. In this session, we are going to understand how a model finds out how to improve or which way to move, and why that answer costs and what it does. So let's dive in quickly. Setting out the objectives, we are going to understand how do we understand derivative as a sensitivity. If I nudge a certain input, how does the output vary based on that input, and in which direction is it moving? That's what we are going to see. We're also going to understand how do we assemble gradients. We are going to look at partial derivatives that are stacked into a vector, and how do they point uphill or downhill. We are going to look at applying the chain rule, how the back propagation is typically nothing but a chain rule, and executing that chain rule changes all the compute values. We'll walk a backward pass. We understand forward, backward, and updating them by hand on a paper will show. Uh, we look at pricing a training run. How is floating point operations per token calculated to train, to serve, and we'll look at why it is approximately or roughly three times the serving costs um, to train. We'll also diagnose gradient flows. We'll understand why ReLU, which is rectified linear units, are used. We'll look at residential connections and normalization, and how they are helpful in the long run. So this is the journey that we are going to take today, from a single nudge to the training bill that arrives. We'll look at foundations, where we're talking about sensitivity, gradients, and the steepest ascent. We'll look at the mechanism. When we say the mechanism, the whole flow, the chain rule that we look at, the descent that happens, how training or learning rate impacts the vanishing gradients, are uh, um, um, uh, blasting gradients, where bombarding gradients, where too much happens and too many calculations take place. We look at back propagation, where we are going to look at forward, backward, and update, and we'll try to do this by hand. When I say by hand, I'll show it on the slide and we look at it. Finally, the consequence of why it is approximately three times the cost to train a particular model versus serving it or inferencing it. We're going to look at memory and vanishing gradients as well. So that's what we are going to look at it. And this is the context that we are setting for all of the coming slides. We are saying where the numbers in matrices come from. We already looked at week 1, where we understood what is similarity, and in week 2 we looked at decomposition. And both of those weeks we did not touch on how a model learns. That's what we are going to do today. Here are some of the key terms that we'll keep repeating throughout this session: forward pass, loss, backward pass, and gradients, which we will try to update. And this as a whole loop will keep repeating until the loss converges to the minimum, or the gradient ascent or descent flattens. We don't learn anymore, which is called convergence. So the question that a model will ask is once per weight: hey, if I nudge you a little, does the loss go up or down, and by how much? And back propagation is the only affordable way to ask that billions of weights at once. So we'll also learn why is back propagation the only affordable way. We are also going to look at that. Everything expensive traces back to it. So whenever we train a model or inference from it, all that comes back to these loop. Okay, when we train, how does the forward pass, backward pass happen? How are the loss and gradients calculated and updated? Loss is calculated, but gradients are updated. And finally, this is done in a batch wise, or epoch as we call it. How those iterations are ultimately resulting in the costs that we do as a parameter of learning rate. So we are going to look at that. This whole module is the machinery behind of all this training and inference part. So calculus is the question, and back propagation is the answer that made asking it affordable. Let's start with the sensitivity. uh, whenever we train, the weights that sit in the network are calculated based on how the forward propagation is happening. And at any point in time, we are saying, hey, we are at a certain point and we are trying to minimize the loss. And for every step that we take is the loss maximizing or minimizing. And derivative helps us understand, hey, if I nudge by point x, is the loss incrementing or decrementing? That's what we are trying to learn here. So what is a derivative? It's a sensitivity coefficient. We understand that, hey, if I nudge the input by a tiny amount, how much does the output move and in which direction? Imagine there was a curve and we drew a slope at and this is point in time learning. So we understand, hey, at this point in time, how much is the learning happening? But here it's all in deltas. That is, if I move this x naught point to x naught plus delta x, how much is my function value changing, which is delta f? And that is the measure that we are interested in. If I improve something by delta x, how much will my total loss change or increase or decrease? Yeah. And that's the question from what is the slope here, and it is the one that training actually asks. Yeah, the sign carries a very important information. Positive means we are increasing the input, increases the output. Negative means the opposite. Hey, we are increasing something, but it's decreasing. Yeah, zero means at this point the input does not matter. It does not change anything in the output. So every weight in a model has a derivative with respect to the loss. Yeah, that single number is the entire content of learning. Yeah. So every time we run these equations and we are trying to change the weights of the model with respect to the loss, we are trying to understand, because we are trying to minimize the loss. So when I change a certain loss, how does the weights in the model change? So imagine the function is like x square. So f dash x, which is the derivative of x with respect to x, is 2x. In this case, if we insert a value of 3, f dash 3 is 6. But f of 3, which is x square, is always 9. 3 into 3, which is 9. Yeah. If I take the f 3.101 square, it will become 9.0601, which is 3.01 square, and the change is 0.0601. Yeah. But if I take a derivative, which is 2x, yeah, and I put 3.01 here, I get 3 2s are 6 into 0.01, which is much higher compared to than just 0.0601. Yeah. So what are we trying to say by that? Yeah, a weight whose derivative is large is one the loss is very sensitive to. Yeah. So this is what is important. Yeah, anytime that derivative is large, the weight, the weight whose derivative is large is one the loss is very sensitive to. We should be very careful if we are trying to train parameters whose weight is also very large, because their loss also will become very sensitive to that, and it also grows in proportion to that. Yeah. If the weight whose derivative is 0, will has a stopped learning entirely, because for every loss change it is not learning anything. Yeah. So derivatives are not abstract. Yeah, they are a prediction about what happens if you change something, and you can always check them back with arithmetic. Yeah. So two readings of the same number is what we are saying here. The slope of the tangent that we looked at geometry, yeah, it's a straight line. Yeah, it's touching a curve at one point. It's the instantaneous rate of change. It's used particularly in physics. It's the velocity recovered from the position and so on. Yeah, it's correct, but it's not useful here. Yeah, neither framing tells you what to do next. But a sensitivity coefficient, which you says that, hey, if you nudge the input, the prediction how far the output moves is very important for us. So that's the sensitivity coefficient that we are talking about. Yeah, and it's a blame assignment. Yeah, how much does this weight contribute to the error we just measured? Yeah, we can pinpoint and say, because of this particular weight, the whole system's output is changing. And there is one particular number that matters to a product manager. yeah, which is whether it's a dead weight or not a dead weight. Yeah, because if the derivative of 0 means that weight has stopped learning, any change in the input does not produce any change in the output. Yeah, so when it happens to a whole layer, you have a network that trains without improving, so it's not improving any further. The run completes, the loss curve flattens. Yeah, we'll see it in a diagram in the coming slides. You spent the whole budget but got a mediocre model. Yeah, so nothing in the log says why, because you have not understood why it's happening. Yeah, the objective is that we notice it in the first week rather than week 4, and that would save us a lot of a great deal of money, because 3 weeks of training will obviously be stopped. Yeah, so when a run underperforms, ask what gradients look like before asking for more data or a bigger model. That will save us a lot of cost. And now that brings us to gradients. Yeah, while one derivative provides us a change in the output for every change in the input, if we stack them all into a vector, that gives us the gradient. Yeah, that tells us whether we are going up or down in a hill which is in a n-dimensional space. So imagine there is an n-dimensional space and you have a function like this, f of x of y of z, where x, y, z are 3 dimensions. Yeah, and you have a function that you have derived for this whole plane, which is x square y plus sine of yz plus 3z. Yeah, and with respect to x, if you do the derivation, it is 2xy, and if you do with these two become 0, but if you do it with respect to y, we'll have these two functions, this becomes 0, so which is x square plus y comes out, and it is change in sign becomes cos, so z cos z, that's how the function translates, and 3z becomes 0 because there is no y component in this. With respect to z, this becomes 0, so we have y coming out, so it's y sine of yz becomes cos of yz, which is the derivative of that, so it becomes y cos yz, and plus 3z becomes 3 because the derivative of z becomes 1. Yeah, so these how the constants are arrived at. Now these are in 3 dimensions. Imagine there was n dimension and you're stacking them one below the other. So derivative of the function with respect to x, dou f by dou x, yeah, like this, you stack all of them with respect to n dimensions, then that gives you the n dimensional vector. Yeah, and for a model, that means one entry per weight. Every weight that we have would look like this. The function of dou of L, which is a loss function, by dou of W1. We are uh, we are differentiating it with W1. Yeah, so n dimensional vector, the gradient comes like this. So this is the function, this is with respect to the loss function. So the gradient of a 7 billion parameter is a 7 billion dimensional vector. So there are 7 billion parameters, and each of that parameter or weight gets a corresponding element in the gradient when we stack them together as a derivative, and that becomes these many number of dimensional vectors. Yeah, and every training step that we execute is actually consuming this. Yeah, and yeah, that's what it says. Yeah, every training step computes a gradient the same size as the model, and that is why gradients cost roughly as much memory as the weights do. So as many weights are there, that much memory would be required to store all these numbers. So that's why the same compute would be required. Yeah, and we just looked at a similar function, but when it is dou f by dou x, dou f by dou y, we get certain values when we place x and y. But if you take the absolute value or length of this vector, you will get 8.06, and that's a magnitude. Yeah, and this also matters because at the end of the day we are trying to minimize this as well. Yeah, so that's what it says. Two numbers, two sensitivities. Moving x is worth 4 while moving y is worth 7. So y is a little more impacting the whole gradient than compared to x. Yeah, at this point the function cares more about y than about x because it's worth more. The magnitude matters too, because when we take the absolute delta f, we are getting 8.06. A large gradient means a steep slope. Yeah, and locally system sometimes many a times it cares only about steep slopes and it starts climbing. Yeah, so a near zero gradient means it's flat region, which means either we have reached a solution or we have reached a plateau where the training stalls. Training doesn't improve much, so we can either improve the learning rate there or do other practices to solve the problem there. So a gradient is a rank list in which inputs matter right now and by how much. That's what we are trying to say. So imagine at this point in time, you have a gradient, and when you run the function, it's basically saying, hey, do you want to go up? Do you want to go down? How do we move that? Yeah. So the answer is not toward the answer. We're not looking to move up or down the answer. Yeah, we are saying, hey, we are trying to move up locally, but at the end of the day we are trying to minimize the loss. We walk in the opposite direction. Yeah, we identify the delta L, the gradient, but we identify how much needs to be moved and we move in the opposite direction because ultimately we need to minimize this loss. So we have to come here. Yeah, and it's myopic in nature, as in at this point in time we always see the closest local slope and we don't know what is global value. Yeah, and that could be anywhere between 20 to 30 steps away. When we say steps, it's an epoch that we are referring to. Yeah, and why this limitation reaches your roadmap? Yeah, because training is iterative in nature. Every time we have to run this again and again in multiple steps. Yeah, the learning rate matters so much. We're going to look in a future slide. How much steps do you take from here to reach here also matters, because everything is a cycle, and cycle means compute means burning money on GPU power. And plateaus are operational problems, not curiosities. Yeah, uh, once you have reached a plateau, it doesn't mean that you have succeeded in achieving the most optimal solution. It tells us that we have flattened the training. And the gradient doesn't know the destination. At any point in time, the gradient doesn't know whether it has reached the destination. It only knows that, hey, there is a uphill and I need to climb. Yeah, and our objective when we do the back propagation also, we'll look at how do we do a minus delta L. Yeah, imagine fog on a hillside. Yeah, you can feel the slope underfoot and see nothing else. You still get down, but only by taking many small steps. So what are we saying? A large gradient means steep hill, still far away from a minimum. Yeah, normally early in a run we would see this because there is steep slopes, very high values. Near zero gradient, it means we have either reached a flat plateau or a flat region. Yeah, we need to understand whether is the loss actually low or we are just stuck in the training. Gradient climbing fast, it means it's shooting up. Yeah, updates are overshooting, is clipping on what is the learning rate. We need to understand if learning rate is too high. Gradient near zero in early layers only. We are saying that, hey, within a couple of first epochs or first few layers itself, the gradient is reaching zero. Yeah, the signal is not reaching the bottom of the network. As in, we have started on the left side of the network, but the signal is not reaching on the right side. Yeah, that's the problem we are reaching at. So we need to ask, hey, are there skipping connections? Are there skip connections from the first network or layer? Are there connections reaching to the third layer? Can be designed like that if the gradients are not reaching to the end. Gradients is not a number. This is pure mathematical compute problem. So we need to understand if numerical failure is there in the upstream, which is the left side. Yeah, we stop the run. We understand which batch it was doing this. So gradient norm is usually plotted right next to the loss, and it is usually ignored. Yeah. So let us now look at the chain rule. Yeah, and how does this happen? We are chaining one function inside the other, and this is the only mechanism deep learning right now has to improve the propagation of the data till the end. So we know that, hey, there is an input that's going to come, and this is the model that's training our layers, and we are trying to minimize the loss function, which is denoted by L. So this layer, forward layer F1, and then we have forward layer F2, F3 until FL. there could be L layers. Okay, so when we give the inputs, we are going to train all these models such that the sensitivity of the loss to a weight buried in layer 3 is the product of the local sensitivities along the path from that weight to the loss. So what are we trying to say? Hey, we are trying to chain these such that the uh, sensitivity of loss at a particular weight is nothing but the product of the local sensitivities until it reaches the loss. Yeah, this with respect to loss is a multiplication of individual local sensitivities until the loss. That's what we are saying. And this helps because it multiplies a small compound towards nothing and large numbers compound towards infinity. So it helps us uh, build the gradients such that every model that we will ever ship follows this simple chain process to calculate these gradients at each path. And that's where we take the two roots with one answer. Yeah, if the function f of u is u square, where u itself is a function like g of x, and in this case it could be 3x plus 1, at x equal to 2 u's value will be 7. Yeah, if we do a derivative with respect to u, u square becomes 2u, which is u's value is 7, then it becomes 14. If we do a derivative with respect to x, which is 3x plus 1, it becomes pure 3 because 3x derivative is 3 and 1's derivative is 0. And derivative of x function f with respect to derivative of x, which is 2u, which is 3x. Yeah, and it becomes 3x derivative of f with respect to x, which is 3x plus 1 square. So it is going to be 2 of 3x. So 2 into 3 into what is x in this case? 2. Yeah, that's what we are going to put, where u is 7. So it becomes 7 6a, which is 42, or 7 into 2 into 3. Yeah, which is like 42. And you saw this chain rule, right? df du dx. So 2u into 3. 2 into 7 into 3, which is 2 into 7 is 14, into 3 42. Yeah, we can check this with 6 into 3x plus 1 as well. It's the same logic that we are applying. It comes at 42. And why frameworks are built this way? Because each layer only needs to know its own derivative. Yeah, nothing needs a formula for the entire network, which is what makes composing arbitrary architectures possible at all, at scale as well. So what are we saying by this? We just ran through some complex words, which is we are saying that, hey, composing arbitrary architectures. When we say arbitrary architectures, we are saying that, hey, the layers with which we build these systems can be arbitrary also in nature, and even then we will achieve some possible outcomes from these. And when we looked at this example earlier as well, if the output is a vector f of xy, which is x square y plus xy, then we could take a derivative which is 2xy, and with respect to x, with respect to y, this will become x square, which is here. With respect to y, we saw, and with respect to j, it becomes 1 comma 1. So at 2 comma 1, if we insert the values, we'll get 4 4 1 1. Yeah, and this is the chaining of functions that we are talking about. Yeah, formally backpropagation is a chain rule applied to a chain of Jacobians. Yeah, and practically, as the next slide shows, it never builds one. So imagine we have stacked all of them. We are taking derivatives with respect to each input until the end. Yeah, so we have dou y1 by dou x1, dou y2 by dou x1, and so on until uh, each of the equation is put with respect to derivative each input. That gives us x by x combination. So if x is 1000 4096, we'll have 4096 into 4096, approximately 16.8 million entries. Yeah. So for each of these, when we put them in a matrix, these are called Jacobian sensitivities. Yeah, because for each input we are calculating the derivative of the output with respect to the input. Yeah. And the weight update that we are gonna do also is gonna be of the same size, at least, because we have to update these weights and subtract this delta L. Yeah, we'll look at it in the next few slides. So it's the same matrix seen from the other side, as in how much are we going to subtract it from. So frameworks actually never build them, they compute vector Jacobian products directly, and we never form the J explicitly here. We take the vector, we compute the J transpose V, which is the Jacobian vectors transpose, and the vector that has come in, we get the output vector. Yeah. So the cost of O n square memory is eliminated because we don't have to calculate for all. Yeah, we only calculate for the vector that has come in. So the cost of computation is also avoided. Memory and compute both are avoided. Yeah, full Jacobian will look like this, which is too big, too expensive, and we will never build. So what are we doing? We are taking the second derivatives one level up again. Yeah, and that is Hessian kind of a system that we are building around the Jacobian. Now we learned how the gradients are calculated, but how do we get down from there? That's the descent part. How do we reach to minimal loss, or how do we keep repeating until the loss stops falling, yeah, and we reach a flat surface? That's what we are going to look at here. Yeah. So we understood that whenever we are at a particular point, we will calculate the loss. It will typically point upwards, and we need to take a negative step in the opposite direction. Yeah, the ultimate objective is that we don't climb up, we go down and ensure that at every point in time our learning is consistent, and we reach faster to that place, because otherwise we are computing the whole loop again and again and again. You know, so the new achievement where we are saying we have reached is old minus learning rate into the the lost derivative. You know, it's as simple as that. The new weights equal to old weights minus learning rate into delta L. So new weight equals old weight. Yeah, we looked at it. The gradient says which way is uphill. We minus the sign, turns it around, and the learning rate decides how far to step. Yeah, each step, and that line repeated is the entire learning algorithm. Yeah, this loop is entire learning algorithm. We have initial weights to begin with. Sorry, here initial weights to begin with. We subtract learning rate multiplied with the delta L, that gives us the new weights. Yeah, two ways this could go wrong, this whole function. If imagine that step is too small here, and we will do a lot of computes, time and cost and memory, all is going to take a lot. But if we take too big a step, we might overshoot the exact place that we need to land in, and this also overshoots and too many calculations. Yeah, and we are everywhere but never near the destination. So a learning rate that works is, it has to be calculated. Is it 0.1, 0.01, and so on. Imagine f of x is the function and x square is what we have coded as a function there. From x is equal to 4. At x is equal to 4, if we do the steps, each step is contributing some value. Yeah, if we multiply that by 0.8, is 0.8 is a multiplication factor here as we see it. So 3.225 to 2.5, 2.08, 1.6. Yeah, that each fraction of that learning rate is taking us towards 0. So progress is geometric here in nature rather than linear. It's not addition, it's rather a multiplication. So So how do we see it? We see this as a healthy shape, and a loss curve that falls fast and then flattens is exactly where we want to be. Yeah, we want to be seen on that side. It is what you want on the dashboard in the first hour of a run. Typically it doesn't happen, but that's the expectation. Yeah, ideally we do this 4 steps by hand. We then look at first 90 seconds, and then we stop to improve the learning rate there. And when somebody says the run blew up, yeah, this case the learning rate was too large. Instead of just zero point 0.1, somebody would have given a larger learning rate. So it is minus sometimes, plus sometimes, minus sometimes. So the divergence is high and it is oscillating in nature. So this can be avoided by starting small, but if you're not reaching the uh, desired outcome or minimize loss function early, then that increases your time and cost function as well. So there needs to be some kind of a trade-off here. So how do we read the loss curve? We typically imagine if you're if the curve is starting flat from the start, so it'll likely cause learning rate, because the likely clause that we are arriving at is, hey, learning rate could be too small, we are not learning much, and hence it is flat from the start. Or there are vanishing gradients, yeah, because we have already uh, reached the zero for those gradients. Yeah, first question to ask is, hey, what is the gradient norm doing there? Falls, then flattens very early. The learning curve falls dramatically and then falls fairly, which is good. Sometimes it could be a plateau, or the schedule that decayed too fast. What does the schedule look like? We need to look at it. It climbs steadily. This could be a good sign, but it could also be because the learning rate is too large. It keep on increasing. Yeah, can we lower it and restart from a checkpoint? That's a question that we need to ask. So every time you run a model or training, try to always checkpoint it so that we could start at a particular point and see if it goes up or down. Jumps to a nan, we know this because exploding gradients, or it could be due to bad data as well. We need to check if clipping is on, which batch was it. We need to understand a specific batch that jumped to not a number. False, but evaluation does not improve. Maybe we are doing overfitting, or the loss is the wrong proxy. Yeah, what does the held out set say? We need to look at that. 5 minutes, not 3 weeks. Yeah, we are expected to fix. As PMs, we are not expected to this, but we are expected to ask the right questions early enough that someone else from engineering can do something about it. And that brings us to backpropagation. Yeah, one tiny network that we are trying to use, the 4 numbers that we will see, and how we can do this completely by hand. Yeah, imagine the whole network is a collection of these lines. Yeah, h is the heuristic function that we are looking at, where w is the weights and x is the input, and that's linear in nature. And a is a function that is a rectified linear unit of h. Yeah, because this is the activation function. Anything from this goes to the next network. So here we are trying activation, which is maximum of 0 or h, where h is w1x. Yeah, and y, which is the output, is nothing but weight 2 dot a, which is the rectified linear unit, and again this is linear in nature. Ultimately the loss function is y minus t, the whole square. That's how we are looking at this whole loss function from input to output. X is the input, y is the output, L is the loss. So 4 operations that we are trying to do. Everything a large language model does during training is this. Yeah, four if I can say, 4 calculations. Yeah, and repeated across billions of weights and trillions of tokens. Yeah, nothing conceptual is added, only scale. Yeah. So imagine there is a forward pass, and in the forward pass we have x1, w1, w2, and target is equal to t. Yeah, target as in the output variable that we are trying to achieve, our truth value. So in a forward pass, we know that h is equal to w into x, which is w1 3 into x, which is 2, is equal to 6. At a rectified linear unit of 6 would be 6 in this case. y is equal to w2 into a. W2 here is yeah, w2 is -1 into a, which is 6, is equal to -6. And y we learned, or the loss function we learned, was y minus t the whole square. Y is -6 minus t, which is 1 square. -6 minus 1 is -7. The whole square is plus 49. So loss is 49. Yeah, it is not badly wrong, which is exactly what we want for a demonstration, because the fix will be dramatic. Yeah, we need to fix this. The loss is very high, we need to reduce this. So keep every intermediate value h, a, y, we need to store them. Yeah, because we are going to update them in the backward pass. Yeah, holding them in the memory is where training RAM goes. We have to hold these three numbers uh, in the memory. When we come to the 6th week, we'll look at how it would cost us to store all of these in a memory. Yeah. So then in the backward pass, we need to derive that whole function, loss function, with respect to all these variables, which is with respect to y, with respect to w2, with respect to a, h, and w1 as well, which is in this case h dot x. So we do that and we calculate the values. Yeah. So a rectified linear unit, which is in this case we saw, which is w1x. Yeah, sorry, here it would be 0 and the gradient would stop dead at that unit, and that is the dead rectified linear unit problem visible right there in the arithmetic. So we need to be very careful about this, because if you are not improving, then no fun in running the loop again and again. Yeah. Now we need to update it back. Imagine the learning rate is 0.01. Yeah, and we looked at each of these functions. These are the values. So we do 0.01 into 84, which is this 84 minus 84. We multiply and subtract. The subtraction became addition here. So -1, which is old weight of w2. Old weight of w2 was -1. And if you remember, this is the function that we are trying to apply. W new is equal to W old minus learning rate into the loss function value. So loss function value we arrived at 49. Yeah. So we did these calculations, and 0.01 into 84 uh, minus, so plus 0.84, w1 w2 old was -1, so we add it, we get minus 0.61. w1 was earlier 3, if you remember. W1 was 3 minus of learning rate 0.01 into loss, which is in this case your 28, the last one with respect to w1, 28. So we subtract that and we get 2.72. Yeah, so this is the back propagation that we did. Now if you do the forward again, we'll get this values. So now you see the loss function 3.94984. It is not 49 anymore. So there is a steep loss function reduction from 49 to 3.49 or 3.50. Yeah, in one step itself we reduce the loss from 49 to 3.50. So our learning rate is also correct. Yeah, now we just need to run this loop again and again, a few, I don't know if it is millions, billions, or trillions of times over a few trillion tokens, but that's what we need to do to get the right weights. Yeah, and that brings us the language model, and that's all there is to large language models as well. Yeah. So if a student can remember one slide from this week, make this one. Yeah, recompute the forward pass live rather than showing the finished results. This is how the multiplications are calculated. And why it has to run backwards, this is the whole slide that explains why. Now imagine there are so many layers and you do the forward pass. Now it's easier to update all the weights in a single go. Otherwise it would take a lot of time to compute the losses from forward. Yeah, so back propagation in a chain rule makes it much easier for us to update the weights. Yeah. And that brings us to the two ideas that always travel together. We are saying back propagation is the computation of the derivatives. Yeah, it answers how much each weight contributed to the error. Okay. it is exact. There is no approximation or no search or no random. It is purely mathematics. Okay, and it's a predictable cost. After for every one forward uh, pass, there is twice a backward pass happening. So it is twice a forward pass. The cost is twice a forward pass. And how does this help? It helps in gradient descent. We are learning, we are understanding if the learning is happening or not. Yeah, it uses those derivatives to change the weights. So we are using those derivatives to go back and make the changes in the weights. And it's approximate and iterative. Yeah, it needs the learning rate, a schedule, and a certain amount of luck. Yeah, I would say we can remove that, but yeah. So that brings us to this interesting topic of, hey, how much is it gonna cost us to train, yeah, the forward pass, that backward pass, and how much would it cost us to inference? Yeah, two numbers that we will always think in terms of is 6n and 2n. Let's look at what they are. Forward mode costs one pass per input. That is, you send the inputs and you have some y is equal to mx plus c kind of a calculation that needs to be done, and that needs to be done. So there is two calculation that's happening. Yeah, which we saw is something. Sorry, where is this? I don't know where we saw that, but there is one multiplication and one addition happening. So we are doing two calculations. So for each of those n parameter model, we are doing 2n compute. Yeah, this forward pass. Yeah, forward pass, one multiplication and one addition that we are doing. Yeah, so it's two computes that we are doing. And to be very precise, wow, where is this? I'll try to show it towards the end, but there are two calculations that we are doing, and that's why it costs 2n. Whereas in the back propagation, yeah, here it is, sorry. So 2n, y is equal to wx plus b. We looked at this, and in backward propagation we need to do 4n, because we looked at gradients with respect to input that we need to do, with respect to the weights that we need to do, and then the parameter updates. Yeah, well, where there was one multiplication and one subtraction. When we say the parameter update, w new is equal to w old minus learning rate into delta L, which is one multiplication of learning rate into delta L and one subtraction, which is w old minus learning rate into delta L. So that's 2n. And we need to calculate the gradients updates with respect to input and with respect to weights. So that's n. So that's why in the backward pass there is 4n calculations. So imagine we are doing a training, which is one forward pass plus one backward pass. So approximately 6n calculations or numbers are to be calculated and saved. Yeah. So, but inference is only a forward pass. You give it, it gives an output. So which is like 2n. And that's why training is 3 times the cost of actually serving, which is inferencing. Yeah, and all these are calculated in flops, which is floating point operations. Yeah, we are saying this is roughly 6 times the parameter token parameters times tokens. Yeah, so this again needs to be multiplied with the number of tokens that we are doing this for, and that's why training is more expensive than actual inference, approximately 3 times. And where does the training memory actually go? We are looking at the weights, the gradients that we need to update, the optimizer function, the activations in the forward pass. We are looking at the number of batches that we need to calculate, the whole sequence, and the layers. So this is where the whole memory goes. And these are totally two different businesses, because if you calculate about flops, it is about 6n, this is 2n. Are the weights held in memory? Both, yes. But the gradients, yeah, the gradients that we are calculating is in training, it's one per weight. Here, nothing. In inference, we are not calculating gradients because we are not going to update them. Optimizer states yes, here none. Here activations are retained yes for every layer. Here it is also none. Yeah, so training and inference are totally two different businesses. Training takes approximately 3 times the compute of inference for one batch or one epoch. So, and this needs to be done trillions of times or billions of times. So based on the number of tokens that we are passing. So how does that happen, or how much will that? We'll look at it in part 6. So checkpointing is one aspect that we could do, so that we store the memory until that point, and then we change the weights, um, we change the learning rate, we change optimizer functions, we change and all of that. So what we are saying is store only some activations and recompute the rest during the backward pass. The memory will fall sharply. That's called the drop. How you drop certain layers or certain weights. Yeah, compute rises by around 30% because we are doing that activation as well. So it is an option that lets a training run fit on hardware you already have, at a price for a long run. Yeah, why this is a product decision? Because we need to understand time versus money. We can do more money and reduce the time, or we are gonna do it in more time and reduce money. Yeah, so it's a product manager's call, how much budget can we allocate, and so on. Yeah. So when the answer to a memory problem is we need more GPUs, ask whether checkpointing was considered first. Yeah. So what does low rank adaptation solve for? It solves the problem of freezing. Yeah, gradients and optimizer states for the base weights are frozen, and we take a large single block of training memory, and we train them on lower ranks or smaller sizes on one or two GPUs. So low rank adaptation sits along with the frozen weights that we have on the original model. Yeah. So, but what does this does not remove? This does not remove the activation memory, because the backward pass still has to flow through the frozen layers to reach the adapters. So that activation memory, which is much smaller than the total memory, is still required and still needs to be stored. Yeah, on long sequence, that is often what actually blinds, because we forget that activation memory needs to be considered. Yeah. um, this brings us to gradient flow. This is the chain rule that we were talking about from the beginning, and the multiplication is unforgiving. Imagine our learning rate is 0.9 versus 1.1. Yeah, and imagine, I wouldn't say the learning rate, but the weights that we have. Imagine there are 50 layers that we have to go through, and this weight will compound over 50 layers. So it is 0.9 to the power of 50, which is 0.005, 200 times weaker vanishing, versus 1.1. If you put to the power of 50, it is 117.4, 120x stronger approximately. So while zero point 0.9 and 1.1 look close, the depth, which is the chain rule until the end, yeah, the number of layers will do the damage. Yeah, and these are not individual values that get spoiled. It is the number of layers that we have, and this is why depth used to be hard. Yeah, network stopped improving past a couple of dozen layers for arithmetic reasons rather than conceptual ones. Conceptually, the layers are correct, but the moment we pass certain layers, the vanishing gradient starts appearing. Yeah, and solving that is what unlocked the models we have currently have. And two failures that we looked at from two very different experiences. One is vanishing gradients and exploding gradients. Vanishing gradients, early layers where the the signal does not reach to the next layers, and it effectively stops the learning. Yeah, we can recognize this through loss plateaus in the early stages itself. That is, the loss number becomes very small and it stays consistent. It does not increase, it does not reduce. Yeah, it plateaus or flattens there. The run or completes normally. The danger, because it is silent, it does not tell us anything. We'll pay a full price for all the training and get a mediocre model. Here in exploding gradients, we understand that the updates will become enormous suddenly, and weights will overshoot, and the run will fail. And we would have done a lot of compute, but we will still never get the the best model. So loss will climb, then it will go to not a number. Loud obvious, because we'll see the gradient numbers increasing dramatically, and it's easier to fix. Whereas here we don't know whether we have reached a local minima, and we are just sitting on a plateau without reaching the global minima. So four fixes that we can do: use rectified linear units instead of sigmoid functions. We could use residual connections, because adds a route with a derivative 1 highway. The gradient can always travel till the end, so vanishing gradients problem is solved. Normalization, this keeps the activations in a range where the local derivatives stay 1, and this will avoid the exploding gradients. Gradient clipping, a hard cap on the gradient magnitude. This again helps us clip on the this exploding gradient experience. It's crude, but it's effective. Yeah. So the identity doing the most important job in deep learning is this. So the derivative is 1 plus something. We understood this. If you write the residential connection as y is equal to x plus function of x, if you differentiate it with respect to x, you will get 1 plus the layer's own derivative. Yeah, 1 plus the own layer's derivative. So whatever the layer itself does, that one guarantees the gradient reaches the layer below it undamaged. So it's moving on to the next layer. So we can call it a do nothing transformation. Yeah, we remember if you remember this, we said the identity. Yeah, a guaranteed route for the gradients. Gradient turns out to be worth more than anything clever you could put in its place, and it is inside every transformer block you will ever ship. uh, it's a uh, it's a learning perspective. If you see, why do we have to learn this session? Because we understood that, hey, training economics have a formula now: 6n to train, 2n to serve. Memory is a dial. It's not a constraint. um, we could control on how much memory is required through activation memory, through checkpointing, calculating the batch sizes as one connected system. Yeah, you can trade one for another. You can increase the activation memory, you can reduce the number of checkpoints, and so on. The model is not learning is undiagnosable. The model is not learning is diagnosable. Yeah, we can actually check if the learning becomes flat, or is it climbing, or becomes not a number. Each point will tell us something very specific. Yeah, we need to ask this in week 1 and not week 3. Architecture decisions are gradient decisions. Very true, because we are putting ReLU, residuals, and normalizations as fixes for a known arithmetic problem. Yeah, these are not preferences, but known fixes that we are trying to put. The training and serving are different businesses. Very true, because we looked at 6n to train and 2n to serve or infer, and the kind of hardware that is required, everything changes. Here are some misconceptions that we looked at. Backpropagation is the learning algorithm. No, backpropagation actually computes the derivatives. It's the gradient descent does the learning, and these are two separate ideas that have always traveled together. Gradient descent does the learning, which is w weight, w nu is equal to w old minus learning rate into delta L. That's more important, and in that gradient descent is minus delta L. Okay. Deeper networks are strictly better. Sometimes yes, sometimes not. So it is more of, in terms of the chain rule, residual connections exist precisely because naive depth stopped working. So unknown number of layers, vanishing gradients can appear, and the learning could not reach the end layer. So some layers will become totally useless, and hence deeper networks does not mean it's always better. Training and inference cost about the same per token. No, training costs approximately 3 times, and we looked at the calculation of 2n and 6n there. LoRa removes the memory problem. It removes gradient and optimizes memory for the frozen base. We looked at that. Activation memory will still remain, because it still needs to pass through the memory to connect to all those layers. The gradient points towards the right answer. No, the gradient points actually to the closest flat region where it's trying to stand, and that myopia is why learning rates and schedules exist at all in the first place. Um, Loss went down, so the product got better. No, it could be a local thing. Yeah, loss is a proxy chosen because it is differentiable, not because users value it. We'll look at this in week 5. Why does that gap exist? In terms of interviews, these are some of the questions that could be asked. Firstly, very important, which is explain back propagation to a non-technical stakeholder. We ideally should say that while the model guesses, we measure how wrong it was and then work backwards, asking each internal setting how much it contributed. Yeah, and then each of those weights is nudged towards a better answer, and we repeat this loop again and again until we arrive at the minimal loss. Why is training more expensive than inference? We looked at it. Inference is for one forward pass, about 2n flops, floating point operations per token. Training adds a backward pass, which is 4n. In total, 6n it would be costing us to do training versus inference, which is 2n. What is gradient checkpointing and when would you approve it? Imagine we want to store some activations and recompute the rest. Yeah, roughly 30% more compute for a large memory saving. That's the trade-off that we are doing. We approve it when the alternative is renting more GPUs and the schedule can absorb a longer run. Yeah, gradient checkpointing typically means you can put a full stop to the run, pause it, take the activations, and take more time to run this. If you want it to be done quickly, adding more GPUs or renting more GPUs could be the solution. Why do vanishing gradients matter to a product manager? Because it's a silent failure. The run does not crash, it just stops improving. We are burning the budget or we are running the runs, but we are not getting a better model, we are getting a mediocre model. And it is why our architectures look the way they do. The loss is falling, but the model is not better. What is happening? Typical example could be that, hey, we have reached a flat. How does that happen? The loss and product quality are different things. Ask for performance on a held out golden set and on the behaviors we promised, not the training curve. So do not look at this, look at the behaviors is what it's saying. Yeah, does LoRa solve the training memory problem? Partly. It solves partly because you don't have to retrain all the weights again. Yeah, it removes the gradients and the optimizer state for the base, but the backward pass still flows through the frozen layers, so the activations still have to be stored. These are the words that we looked at in this session, which is derivative. It's the sensitivity. How much does the nudge in input predict the output move? We looked at gradient, a partial derivative of the output function with respect to the weights or with respect to the input. Yeah, one partial derivative per input stacked into a vector. The loss function taken as a derivative per input variable, and that stacked into vector gives us gradient. We looked at chain rule, derivatives multiply along a chain of functions. We looked at backpropagation, which is reverse mode auto difference. One sweep and every gradient is updated there. Yeah, activation memory we looked at because forward values held until the backward pass consumes them. So that's really important because usually when the batch size is limited, that's what bites us. Yeah, usually what actually limits batch size, this is what actually limits the batch size, because forward values are held until the backward pass consumes them. Yeah, those values are stored. So w old is stored until backward pass consumes that w new is equal to w old minus learning rate into delta L. So the activation memory is very important there. Yeah. 6n versus 2n, we looked at this, the floating point operations per token to train. 6n is the cost of training versus 2n is the cost of serving. And that brings us to a close on this session. We said, hey, we need to nudge every weight and keep asking if the loss has fallen down. Yeah. This was track A, part 3.